We keep talking about gradient descent when it comes to training a machine learning model. We calculate the gradient, adjust weights to minimize the loss. That sounds simple, right? But what does it mean training a large language model that contains billions of parameters? Does the gradient descent still work the same way it is supposed to be? Absolutely, no doubt about that. You compute the gradients with respect to every single parameter, store optimizer states for all of them. What's the problem then? It works perfectly, but requires a lot of compute power and tens of gigabytes just to hold the training state. It requires GPUs, possibly you need to connect to a data center for efficiently training a model with billions of parameters. What if you are a student or a researcher? You don't have access to a lot of compute power. You just have a laptop. Do you just give up on training a model with billions of parameters? What would you say if I ask you whether you prefer training a model with all the parameters on an expensive hardware or training a model where instead of modifying billions of weights, you only tune with fewer parameters and still get nearly the same result? But how would you do that? The answer is low rank approximation. That sounds fancy. Let's make it precise. We need to understand singular value decomposition first. You know matrices as arrays of numbers, but geometrically, a matrix is a transformation. It takes vectors, moves them, rotates them, stretches them, and compresses them. Singular value decomposition states that any matrix can be decomposed into three operations performed in sequence. Initially, we have V transpose, essentially a rotation. It shifts your input vector into a fresh coordinate system. These columns are orthonormal, meaning they create a perfectly perpendicular basis. Next comes sigma, the scaling phase. It is a diagonal matrix where every entry, known as a singular value, either stretches or shrinks the vector along the new axis. One thing to note here is that these values are non-negative and sorted from largest to smallest. Finally, U provides the second rotation. This step takes your scaled vector and rotates it into its final output orientation. That is the essence of SVD. Rotate, scale, then rotate again. It applies to every single matrix out there, without exception. If you look closely at the singular values, they are not equal, and they are ordered from highest value to the lowest. Usually, a smaller number of these values are large and the rest are near zero. But how does this help us? Geometrically, this means most of the information matrix holds is along this small number of dimensions, and the rest contributes so little to what the matrix actually does. And this is the exact idea behind low rank approximation. If you just take the top R singular values and their corresponding left and right singular vectors and multiply them together, you get an approximation of the original matrix. It is the best possible rank R approximation, and how close it is with the original matrix depends entirely on the R we choose. Let's take the weight matrices from one of the pre-trained models, Distilbert, whose size is 768 by 768, and apply singular value decomposition to see the rank needed while maintaining 90, 95, and 99% of the original information. There are a total of 6 layers in this model, and we take Q, K, V, and outweight matrices, each of size 768 by 768. For a fair evaluation, we take 6 weight matrices randomly among these, calculate SVD for each of these matrices, and normalize singular values. Normalizing singular values makes it easy for comparison on how much each singular value contributes against the highest singular value. And we plot the same for comparison. We plot an elbow line by taking a normalized singular value of 0.1 and highlight the rank. It means the singular values from this rank contribute less than 10% of the highest singular value for this matrix. A normalized value of 0.1 means that the singular value squared contribution is only 1% of the leading singular values. So it contributes negligibly to the matrix total energy. The singular value energy is calculated by dividing the cumulative sum of squares of singular values with the sum of squares of singular values. When we plot this cumulative singular value energy for all 24 weight matrices, we can see how much initial singular values are contributing towards the energy. We then plot the average rank for 90, 95, and 99% of the energy. We can see that 90% of the original energy can be retained by using just 41% of singular values, 95% using 52%, and then 99% using 70% of the singular values. But how are we going to reconstruct the original matrix with reduced parameters? We take the rank at which we get maximum energy with minimum parameters. Let's take 70% of the full rank, that is 537, which gives the 99% of the original. Then we keep only top R rows from the decomposed matrices. If the original matrix size is m by n, then the updated size of matrix U would be m by r. The sigma would be r by r, which means top R singular values, and V transpose would be r by n. The outcome would be approximately the same as the original. Let's rebuild the weight matrix using the R value of 1, 8, 64, 256, 512, and 768, which is a full rank, and visualize them together. With a low rank of 1, the visualization is completely different from the full rank. With a rank of 64, it starts appearing similar to the full rank, yet only capturing near 50% of the energy. With a rank of 512, we are capturing nearly 99% of the energy, and it appears much like the full rank. We started with the aim of reducing the billions of parameters down to just a few thousands. But we are using 70% of the parameters. We are nowhere near bringing billions of parameters down to thousands. That's where LoRA comes in. With SVD, we tried to reconstruct the whole weight matrix, which needed near 70% of the parameters. And at R equals 8, there is reconstruction loss of about 87% approximately. And for reconstructing a weight matrix of size d by k, it requires d times k parameters. With the low rank approximation, we do not reconstruct the whole weight matrix. Instead, we just update the weight matrix. During training, the original matrix remains unchanged and learns weight updates instead. It is denoted with delta. And this weight update matrix is constructed using the matrices, say, B and A. A couple of key properties to remember is that the rank of the product of the matrices B and A should be less than or equal to R. And matrix B is initialized to 0 and A is initialized with small random values, so that delta W, which is BA, equals 0 at the start of training. After training, the weight update matrix is added back to the original weight matrix. With this, the trainable parameter count drops to d times r plus r times k, or r times d plus k. And for calculating the reduction of parameters, we simply divide the total number of parameters with the number of parameters required for LoRA. For a square matrix, it would be simplified to d divided by 2 times r. If we take an example of 8 and the dimension of 768, the number of parameters required would be reduced by 48 times. Here are the few models with the size of its weight matrices, total number of parameters versus the parameters required with LoRA for different R values. But choosing the R value is crucial. How do we choose it? If R is too small, we miss the signal in data. If R is too large, noise starts appearing. With LoRA, we set the R value, and is generally 4 or 8, as suggested in the original LoRA paper, and is tested across the majority of LLMs. If we have to find the R value for this data with a 99% threshold, the dimension only comes down by 70% of the original, as we have seen at the beginning. And this is essential to reconstruct the whole weight matrix. Now, 70% is far from a few thousand, but this is the rank we needed to reconstruct the weight matrix. But LoRA doesn't construct it, it updates. LoRA's choice of R equals 8 is not a guess. It is a measured observation about the intrinsic dimensionality of fine-tuning updates. And that brings us back to where we started. Fine-tuning a model with billions of parameters in a laptop. Now you know how it's made possible. The weight matrices are large. The update is not. And SVD is the reason you can tell the difference. We started with asking how a model finds its direction, the calculus, the gradient, the geometry of change. We saw what happens when you apply the geometry to the problem of scale. Whether you are training from scratch or fine tuning with LoRA, gradient descent is the engine behind. In the next episode, we build it from scratch, derive the update rule, implement it in code, and watch it actually move down a lost surface. No shortcuts, no library calls hiding the math, just the algorithm written from the ground up. So you understand exactly what happens every time a model takes a step. If you have missed the last video on what is a gradient vector, you can watch it here. If you want to run the code for yourself, a link for the Python notebook and companion blog post is in the description. I'm Pradeep. This is Decoding Complexities. I'll see you in the next one.